So without further ado, let's thank Roy.
Thank you. So, hi everyone, my name is Roy Shadmon. I'm a 4th year PhD student under Owen Arden. And thank you for coming to my advancement talk, and I'll be talking about proximal Byzantine consensus. So let's get right to it on an example. So let's consider a temperature regulating application for a generator. We have a generator here and it has some temperature sensor from it. And the sensor is outputting asynchronously to a node. And the node is asynchronously processing this data, running some function on it at some output interval. And then it's putting its decision to a thermometer or a controller that essentially decides whether we should turn on the air conditioner or not. And so the red here just signifies that the generator is hot, and green is just that it's at a good temperature. And so the point here in this setup is that the node is asynchronously processing data. The node is going to produce outputs in intervals based on the data it received in the time period. The path that the data comes to the node could be noisy, and this could also be from the node to the controller. And there's also could be transient network faults that could happen in the setup as well. And so let's first start with some bad scenarios of what happens when we only have one node. And so at the output deadline, the temperature readings could be dropped or delayed. And so if we have our setup that we had before, this time the bad temperature, its hot temperature reading could drop. And the node might think, oh, the generator's at an okay temperature, and then decide not to turn on the air conditioner in the room, and this results in the generator exploding. The next bad scenario that could happen is that a cooling instruction could be dropped from the node to the controller, and this could cause the controller to not turn on the air conditioner, and this leads to some cascading effects, but the consequence of this is that the generator also catches on fire or explodes. So another bad scenario is that noise could be introduced to the system, and this time the generator, its hot warning is being sent to the node, but that message is maybe bit flips and causes the node to observe just it's okay temperature reading. And this might cause the node to say, okay, well, we don't need to turn the air conditioner on, the temperature of the generator is fine. And that means the air conditioner is turned off, and again, this could cause the generator to catch on fire.
And then it was going to explode.
Or explode, yeah.
I knew it was going to.
And the final one is the node could become compromised. So this time in our setup, we have it's very hot temperature readings, and this is actually received by the node, but the node becomes compromised, and it just tells the controller the temperature in the room is fine, and the generator again explodes in this scenario. And so how can we overcome these challenges? And the one way we can do this is via replication. And so we want to replicate the processing node. And so ideally, replication in a noisy environment contains some sort of redundancy. So we have a set of we have sensor readings that are sent to a set of processing nodes, and these messages could be noisy. So you can see here the examples all the messages are possibly inconsistent that the processing nodes receive.
I'm just trying to are the sensors replicated too, or not?
I guess they could be.
Yeah.
Yeah. I was trying to simplify the problem, but we'll see that a little later.
We looked at both. Roy, do you want to come over to this corner just so
Yeah.
the majority of the quorum of your committee can?
Yeah.
And I'm sitting here because of the.
No.
I'm sorry. I could have just moved, but.
No, you're good. So the point is that the nodes are receiving an inconsistent view of the data, and so that causes them to be inconsistent. But ideally, there's just some magic function that results in them forming some sort of consensus and resulting in the output that we should turn on the air conditioner to a certain value. So we should turn on the AC to 55 degrees, and the AC is turned on and everything is fine. And even if some of the messages could be dropped, this should only have a marginal effect on the decision that these replica sets are making. So maybe that just causes them to turn the air conditioner on to slightly higher temperature or something like that, but still the air conditioner should turn on in this scenario. And so the point is that this is not a realistic solution because the magic function doesn't really exist. And one of the big questions is that how do you know the decision that these processing nodes is correct? Can you ensure that these processing nodes make a timely decision, given that they have to do some sort of consensus and communication? And if you do consensus, then consensus by an interval can often cause a deadline miss, and could have cascading effects on the generator itself. And so we asked ourselves, how does PBFT, practical Byzantine fault tolerance, handle this scenario? So the output time, the same setup, these nodes are asynchronously processing noisy data. And at the output time, they might have to run some Byzantine agreement on the log that they received. And once they form a consistent view on the log of inputs they all received, then the primary node could run some function and decide that the output is 57 degrees Fahrenheit for the air conditioner. And these nodes can all validate that this is the right value because they all received a consistent view of the log, and they also all know the function. And so they can validate that this is correct and say, okay, I agree with this. And then the leader will say, okay, let's commit it. And they will all send the 57, a consistent view of the data to the controller. But this approach could be possibly time expensive. They first have,
What was f of x again? I didn't get it.
sorry?
What was f of x again?
It's a function.
It's a function.
So the processing nodes receive a set of inputs, they form agreement on a log, and then there's some function that decides based on the values they received what the decision is.
I see.
And in this picture, it was just the primary applied the function.
Yeah, the primary would apply the function in PBFT.
But the other replicas are also applying the function and comparing their results?
They could validate, the way they would agree to this is by saying, well, I can run the function too, because I also have the log.
Yeah, I mean, I guess one of the takeaways here is that they could reach consensus on the log, reach consensus on the output, or both. But you know, either way, they're all doing the same thing and checking each other.
But the leader could initiate that I computed it first, and you can validate before you would send the okay, I agree. And so the point here is that this could be a time-expensive process. You first have to run a Byzantine agreement on the log, and then on the final output. This also relies on a single leader to initiate this process. And the accuracy of this result is dependent on the serialization done by the leader. And so we also looked at another approach called exact vector consensus. And this is a slightly different consensus approach. But you get the same setup, so nodes are asynchronously processing noisy inputs. But this time they all run a function right away. And it's the same function. And when they can compute that function, they will all broadcast that output to each other. But the point here is that this function could result in nodes producing a different output. And essentially how exact vector consensus works is that in every stage you run a function, and eventually you will converge to an exact point. And you continue this process until you will all agree on the value, and then you will all notify the controller that 57 is the right answer. And again, this approach is also potentially time expensive because you have to do multiple broadcasting rounds. This approach has some benefits in that you don't have to necessarily rely on a single leader. But the point that you get to might not be a good point or the best converge point.
Could f of x be like the average of all the values?
Yeah, f of x could be an average. Yeah, essentially any function that takes that does an aggregate. Yeah.
And there's some specific ones with particular guarantees, right?
Yeah.
So PBFT is, the word consensus in PBFT is meaning something different than consensus and exact vector consensus, I think. Because exact vector consensus clearly, with all those F's, is designed to ensure that all of the inputs are considered. Whereas at least, PBFT and consensus in general, doesn't work that way, and you're sort of retrofitting it, I think, to work that way. So I guess, sorry, let me turn this into a question rather than a comment. And it's okay if you don't have a ready answer for this, because maybe you haven't thought about it, but like for PBFT, the reason that it might be time expensive, among other things, is that FLP means that it could take an unbounded and unpredictable amount of time. It seems like this might take an unpredictable amount of time too, but probably not because of FLP. My question is like, does FLP apply to this kind of consensus?
So in exact vector consensus, the guarantee is that their convergence is finite.
It's finite. Okay, so then it doesn't apply, and it seems like it wouldn't apply because this isn't really consensus. It feels like a different thing.
Yeah, I will. You're actually right on it.
Okay.
I'll have a visualization, I think, in 2 slides that will make it more clear. So the point that we're concluding here is that exact consensus is not applicable in noisy environments. And the next best thing you can do is what about approximating consensus?
Mhm.
And so the goals of approximate consensus is that you have a good boundary and a bad boundary. And you want to define your good boundary as the non-faulty points. So all the points proposed by non-faulty replicas. And even if you get a faulty point that's in the bad boundary that's trying to get you to converge into the bad point, you want to avoid resulting or converging to a value in the bad boundary. And you want to make sure that you will converge to some point within the good boundary. And this is kind of, I think, the point that you were making. And so let's first talk about approximate Byzantine consensus. So this problem was first designed in the paper, the Weak Byzantine Generals Problem, and it was formalized in the paper reaching approximate agreement in the presence of faults.
Mhm.
And the paper essentially states that eventual convergence on an approximate scalar value is possible, and it's possible in both synchronous and asynchronous environments. And it states two properties. The first property is the epsilon agreement property. And essentially what it means is that non-faulty replicas will eventually halt on a value within epsilon of each other. And the validity property also states that the consensus value is within the initial values proposed by the non-faulty replicas. And this is essentially consider the good boundary as that I posted in the previous slide as the initial proposed values. And essentially you want to converge on a point within that good boundary.
All pairs are within epsilon? Or
all
all replicas are within epsilon of some average or something?
of each of
All
the
pairs.
final of the converged results.
Oh, okay, so, okay.
Yeah.
Because
So
they
the
they update their values.
Yeah, okay.
Because every round they'll run the function and update.
Gotcha.
But there is a limitation to this work amongst not including is network expensive, is that it only supports scalar values. And so alternatively, there is approximate Byzantine vector consensus. And this was presented in the paper Byzantine Vector Consensus in Complete Graphs. And they described that you can reach eventual convergence on a Tverberg point within the convex hole. And the convex hole is essentially a geometric space around the non-faulty point, which is essentially just the good boundary I showed earlier. And it also works for both synchronous and asynchronous networks. And it states three properties. The first property is that for every dimension, for every dimension of the decision vector that replicas will converge to, 2 points will be within epsilon of each other in the dimension space. The validity property states that the decision vector is going to be within the convex hole of the initially proposed non-faulty outputs or vectors, and termination is guaranteed in finite time of non-faulty replicas. And so let's visualize Tverberg points in 2 dimensions.
Are you going to say what a Tverberg point is?
Yeah, this is
This is it?
This is it, yeah. So you just need a certain number of points, and so in this asynchronous setup, you need 9 points to support 2-dimension vectors and tolerating 2 Byzantine or faulty points. And so the 2 red ones are faulty points. And a Tverberg theorem implies that a Tverberg partition exists with f plus 1 equals 3 non-empty multisets. So if we create 3 multisets, then we're guaranteed to have a Tverberg partition. And any point within that Tverberg partition is a Tverberg point. And so here we have our first multiset. And the reason why we connect 3 dots is that we have 2 Byzantine points, or 2 faulty points. And by having 3 points, we can guarantee that at least 1 point is not faulty. And so we create 3 multisets. And then the intersection of these points is the Tverberg partition. And any point within this partition is a Tverberg point and a valid consensus decision that the system could reach. And so we can state this a little bit in 1 dimensions as well.
Replication, though.
Yeah.
What could be the intuitively the 2 dimensions? For example, it's a 2-dimensional space. What could they be represent the 2 dimensions?
Like type of output. Like
each dimension, is it some kind of signal? Is it?
Yeah, it could be signal. You can think about it as like coordinates, like XY coordinates.
And is the temperature reading or?
It could. So if you say temperature is correlated to pressure, you could take two of those signals in 1 vector.
Can it be like a latent space, for example?
What do you mean?
Like maybe you have 10 readings, like, and then
Yeah.
you project that into a lower dimensional space, or like 2 or 3 principal components. Could it be
Yeah, I
like-
think that the only requirement is metric space. As long as it's a metric space, it's fine.
Uh-huh.
I think.
Because these points lie on a space, right? The
Mhm.
locations matter, right?
Yeah.
Uh-huh. Uh-huh. Thank you. Yeah.
So Schroeder theorem states that if you have at least n points, and then the intersection of partitions containing f+1 multisets is guaranteed to be non-empty. And so this time let's visualize it in one dimension. And so if we have 4 points, notice how we have an extra point. If we have 4 points, we can create a convex hole around 2 points because we have one faulty point. We only need to draw our convex hole around 2 points. And we can say that a Schroeder point is anywhere in between A and B because that is an overlap over 2 multisets. And even if we lose one of these non-faulty messages or any of the messages in general, so let's say we lose B, we still have a Schroeder point, right? So the minimum is 3, so D plus 1 times F plus 1 is 3. So we had 4 initially, now we have 3, but we're still guaranteed, even having the 2 outer convex holes, to have a Schroeder point, which is A.
Why is oh, never mind. I see.
Because they could
No, you have a multi-set if you have people proposing the same thing, which is great.
Yeah, exactly.
And you want it to be strong, yeah.
Yeah.
Right.
And the key limitations of Byzantine vector consensus is that you have this dependency on inter-replica coordination. The consensus guarantees under noisy scenarios is actually rather weak. And the reason is that the more noise you have, the larger your convex hole is.
Mm-hmm.
And when the larger the convex hole is, you also lose your uncertainty guarantees because all the values in the Schroeder partition are treated equally. So they're all valid points, and there's no better point than another one. And the downside here is in this example is that if the Byzantine or the faulty point could essentially pick any point inside here to kind of force convergence on it. And so no matter where it picks inside this boundary, the one point can kind of force convergence on there. And so their attack surface is the boundary between the non-faulty points.
Makes sense.
So the third partition is in green, right?
The Schroeder partition is actually just the overlap.
The green is what?
The green is
the
a
convex hole of
the green is a
of
convex.
the
correct.
It's the convex hole of A and C. Is the green, and then in this boundary is just the convex hole of B and C.
So that's the third partition, just the dotted.
Is the intersection, and
Right.
and this point could actually create another Schroeder partition. But you see, we still conclude somewhere
So
inside.
why it's an attack surface? Because I thought that the green points are still good. Like as long
Yeah,
as you
Right, but the
green-
attacker can influence the final value.
Yeah, they can.
That's how much influence they
But
have.
why does it matter? Because you're still within the green region.
Well-
It's safe, no.
So they value all the points inside this green area as equal, but obviously one point is going to be better than another point. One decision could be better than another one.
I mean, and maybe the way to think about it is that you should only apply this algorithm to problems where however noisy the honest nodes are, anything in the convex hole is okay, right? So if there's any generator explodes points in that space, you can't use this approach.
But like, if what we were monitoring was financial markets or something, there might be an advantage to an adversary influencing between two fine consensus decisions. There's one that benefits the adversary, and they should be a hidden variable, right? The adversary's decisions shouldn't be able to influence it. So this is where they can maneuver.
Also, the census could be price of a stock.
Exactly.
At each point, I think.
Yeah, so giving adversaries choices is bad in general, I think. Unless there really is no difference between.
Yeah, and an ideal thing, you'd say, no maneuver, the adversary can't with high confidence make a maneuver that will influence the result, even if we've restricted the results to ones that are plausible within the hull.
Do I understand correctly that the more noise you have, the more the green area is?
Yes, right, exactly. And so as the noise increases, there's a larger convex hole and more attack surface for the attacker. And so the big question of the research is, can we pick better points with less coordination? And so what do we know? We know that the majority of points are honest but noisy, and that a subset of these points are malicious. And so can we infer the right point directly? And the key idea of the research is that honest processes behave similarly. And if we can model non-faulty outputs probabilistically, then if we can create a deterministic function where given the same inputs and the same probability distribution of the outputs domain, then we would result in a consistent output. And the goal the overall goal is to identify the quorum of non-faulty replicas and then compute the output most conditionally likely directly. And so this is where proximal consensus comes in. And so if we can imagine those non-faulty outputs as some value from a Gaussian distribution, and so all the points are samples from this Gaussian distribution with the same mean and standard deviation and variance parameters. And if all the points are samples of that distribution, then we want to pick a subset of the outputs that we received, and specifically of size 2f plus 1. And then the client's task would be to find an x comma q pair that maximizes the conditional probability. And we can state this this definition of proximal consensus, and essentially how you can read this is that we want to iterate over all possible values in the output domain, and alongside that we want to consider every possible 2f plus 1 quorum, and then we want to return the value that's most conditionally likely.
Sorry, what is the distribution of Q? QI?
Of QI?
Yeah.
QI are samples from the Gaussian distribution. So they're just points from this distribution.
And so is X.
X is the random
I think
variable.
is the symbol you should have there is like QI is in X. These are like draws from the random variable X, I think. Is
Yeah.
what it means. I forget how do you write that in statistics notation, like an arrow?
I'm still not understanding what.
I thought
So
it was-
X and Q are independent?
So Q is a Gaussian random variable. Or sorry, Q is the set of outputs. Big Q.
Yeah.
X is a domain of the Gaussian distribution. So think about it as X is defined by a Gaussian distribution with parameters mu and a variance. And QI is a value within the output with the outputs, set of outputs. And all those outputs are some sample from the Gaussian distribution that we define.
So each QI in big Q is a observation of X.
Yeah. Does that make sense? So another way to think about it is each QI is just a random sample from a Gaussian distribution.
Yeah, why is Q and X, why are Q and X dependent?
Here?
Yeah,
So so we want to find the most likely value given the.
no, I
given-
understand that, but I
think,
don't understand why they are dependent.
Okay, aren't you missing the noise component here?
So they're dependent because we want to figure out the value that we are estimating using this quorum. So they're dependent in the sense that the values X, the value that we're considering X is something we can infer using this quorum.
But Roy, the way that we usually represent this is that Q is drawn from a product distribution that has the actual output distribution scaled by a noise distribution,
Yeah.
and that's all that you can observe. And what you're trying to do is recover the most likely X that caused those observations.
Right. So I tried to
So
simplify
there is
that.
there's another distribution that is not shown in the slide.
So essentially what
Okay, because my point is if Q is a subset of the samples from the normal,
Mhm.
and all the samples are independent, then Q is independent from X.
I see what you're
And the
saying.
conditional of X given Q is just the unconditional of
Okay.
X, and so
So yeah, I'll
you're not learning anything, right?
Yeah, right.
Yeah, so I tried to simplify this, but maybe I oversimplified it. So the point is that the values in QI it's one correct value associated with some noise distribution on top of it. So it's an X, and then a sample from a noise distribution that is multiplied onto that X value, and we have multiple noise values sampled. And
So Q is equal
over-
to X times epsilon I, and epsilon I is being
Yeah.
sampled from, say, an exponential.
Yeah. Or yeah.
Yeah, usually we have a Gaussian with a mean 1.
Yeah.
And it's
We-
the variance is kind of showing
I didn't want to change the sign, but okay, that's why I chose.
but yeah, that's
Yeah.
the.
So the noise is multiplied by X.
So
Right.
yeah,
Yeah,
It's not
so,
added.
so it's a product distribution, yeah, we wanted we felt like that was a little bit more accurate model for.
Yeah.
And it
Yeah,
turned
yeah,
out,
yeah.
once we learned enough about statistics,
It
we figured out how to do it.
Yeah.
I don't think that we've learned enough about statistics, but we're struggling, but,
sorry, are we on the same page now?
sure.
So
And what is at the end, what do you mean by PC of Q and an F?
So this is the definition of proximal
Approximate
consensus. So given a set of outputs, the number of total values you have and the number of Byzantine values you have in Q, then you can compute. You basically iterate over all possible solutions and all possible 2f+1 quorums, and you want to compute the argmax, the value that's most conditionally likely.
I see.
And I think the next slide will show this a little bit more visually. So intuitively, let's say we have 3 quorums. We want to consider over all the possible outputs of every and graph or compute the conditional probability of each possible quorum. So in this example here, we want to conclude that the ideal quorum is Q1, and we want to conclude that the value is 5, because Q1 at 0.5 is most conditionally likely.
And so implicitly, the other curves are noisier or less likely in aggregate because
They most likely have a non-faulty point, or a faulty point in them,
or just noisier data.
or just noisier data.
But how can you tell? How can you tell that the gray one doesn't have a faulty?
So
Because it has the highest.
it's most conditionally likely, and the variance is lower.
Oh.
And are you trusting, like, are you modeling any of the actions of the attacker probabilistically here, or are you what assumptions are you making about the attacker at this point?
So the attacker. So I think this is the next slide.
Okay. You know what you
So it's in a couple slides. I think it'll be clear. So computing the conditionally most likely output with proximal consensus is essentially the replica set gets a set of noisy data, and the replicas compute a decision on what they think the controller should do. But this time, without doing any consensus at the replica set, they directly output their opinion to the controller, and the controller uses the distribution of the output domain and computes the consensus value. And so this is how proximal consensus does this.
So here the replica set is just doing some kind of aggregate
So they're-
computation, but then just outputting it.
They're doing an aggregate computation on the inputs and computing what their opinion of the result should be. So they're saying, my opinion is, so the top one is saying, I think we should turn the AC to 58 degrees Fahrenheit.
Just another clarification, the quorum we've been talking about so far is basically a random subset of the values of a cardinality 2f+1. Something
Not random.
Not
No,
random.
It's selected to be the argmax quorum.
We consider all possible 2f+1 quorums. And
and take the max.
So we're
And
trying
we
to
take
we're trying to find the quorum that results in that peak.
And this is the argmax. That's basically the map, the maximum a posteriori of x
Yeah,
given
exactly.
Q.
It is. Yeah, it is.
And so we conclude, so the point is that the controller computes the consensus value given its inputs. And so computing the conditional probability directly is challenging. And the reason is that just because we know the output domain distribution, we don't necessarily know the conditional relationship between those outputs. And so the way we get around this is by approximating the conditional probability calculations.
Hey, could you say why don't we know the conditional relationships?
We don't know the conditional relationships because we don't know the noise, how much noise each value is essentially getting multiplied to. But we just know that there is some sort of noise added to the values.
And also one of them would be the attacker, right?
And one of the
Yeah,
points is
yeah.
also the attacker, so they can try to leverage that noise to force a bad decision.
And I guess there are two. I think Peter had a question about whether the sensors are replicated too, and So it could be that each output is a separate sample from X, which would make us know even less, or it could be one sample that's perturbed by the different noises, where it would mainly be the noise that we wouldn't know.
And so the way we calculate the conditional probability, or approximate it, is through a similarity metric. And so this idea was inspired from the paper Probability from Similarity. And essentially we can define the conditional probability as the independent probability of a candidate event to the alpha, where alpha is a 1 minus sin divided by 1 plus sin to the power of 1 minus to the probability of the entire quorum. And this similarity function has a really nice property. And so essentially the way we calculate it is that it's a distance and likelihood metric on the space of 0 and 1. And so as similarity goes to 1, it means the values are closer together and they're more similar. And as we go towards 0 on the score, then the values are less similar to each other and they're further apart. And the equation itself has a nice property that as similarity goes to 1, meaning that the values become closer together, then alpha goes to 0 and the conditional probability of that event goes to 1. And essentially what this means is that if the values are exactly the same, so they're consistent with each other, then we have 100% confidence in output. And as similarity goes to 0 and alpha goes to 1 and the conditional probability goes to 0, which essentially means that as the more noise those outputs have relative to each other, the less confident we'll be in the consensus results.
But you do know P of Q.
Yeah.
In the X1.
Yeah, we know P of Q. And we can also use the similarity metric to measure uncertainty. And so as similarity goes to 1, our uncertainty should decrease. So we should be more certain in the value. And as similarity goes to 0, our uncertainty should increase and we should be less confident in our results. But the point that I wanted to make here is that as similarity goes to 1, the variance between the outputs decreases. And as similarity goes to 0, the variance between the outputs increases. And doing it this way allows us to also create predictive intervals on our proximal consensus output. And we can define the predictive interval of the proximal consensus output as the interval surrounding the output itself. And since we assume that the samples are Gaussian and the noise is also Gaussian, we say that the predictive interval is 3 standard deviations to the left and to the right of the proximal consensus value. And this insight is based on the 68, 95, 99.7 rule. So are there questions on that before I move on to next week? Okay, so the next part is how do we bound Byzantine adversaries and how do we limit their impact? And so we can define a Byzantine attack as essentially bounded by the similarity of the non-faulty quorum. And so if we have an ideal quorum A, B, and C, we can say that the worst thing an attacker can do is replace the F largest values and replace them with a faulty point that's less than it. And essentially that would be a suppressing attack. And the point here is that the similarity of phi L has to be greater than or equal to the similarity of the ideal quorum. And it could also do an inflating attack where it would replace the F smallest points with F larger points and essentially force the consensus result higher. But it's bounded by the similarity of phi H has to be greater than the similarity of the non-faulty quorum.
So what exactly do those inequalities mean, like in English?
So the similarity of the
Like
the small quorum of the F plus 1 smaller non-faulty points, including F Byzantine points, must be greater than or equal to the similarity of just the non-faulty points.
So it needs to be at least as
At least as similar.
it needs to look like an honest point.
Yeah, so it needs to look like an honest. So the worst case guarantee.
And the other one?
The same thing.
Inflating attack?
So in suppressing, essentially just forcing the output lower. So if we decide that FL, A, and B is the ideal quorum, then our consensus result will be less than if we decided the ideal quorum is A, B, and C. And if we wanted to force the consensus result higher, then we would replace the F lowest non-faulty values with a higher value. And this quorum just must be just as similar as the non-faulty quorum. So essentially they have to act like an honest point.
But they kick out somebody on the other
Yeah.
side.
but they're bounded by this noise essentially. And so the worst case guarantees is essentially parameterized on the uncertainty tolerance of the system or of the system designer. And so you can say that I won't consider any points outside of the 68 predictive interval or the 95 predictive interval or the 99.7% predictive interval. And essentially you would say all the points to the left or to the right of this interval are too unlikely to happen and I'll just ignore them. And essentially you can have in this scenario two worst case scenarios. The first worst case scenario is where you have a low non-faulty quorum, A, B on the left side of the predictive interval and C on the right side of the predictive interval. And we know that proximal consensus result is less than or equal to the mean of the quorum, given that the mean of the quorum minimizes the normalized distance, which considers both the relative distance between the values and the independent likelihood of those values. And so the Byzantine attacker has, the most control it can do is replace it could replace B with a slightly higher point and force the consensus result higher. Or if we have a high quorum where we have 2 points on the right side and 1 point on the left side of the interval, it could replace D, one of the points on the right side, with a lower value and then force the consensus result lower.
Why couldn't it replace it like all the way at the other end of the?
So it could replace D all the way to something like where B is, but then that would just introduce this scenario.
Oh, I see. But like if it wanted one or the other,
it could pick. And once it overlaps on the consensus result, then it's just the other scenario at that point.
Sure, but that's the case when the attacker made it be that.
Yeah, the attacker could force it. But so essentially, in these two scenarios, the attack surface is, you can essentially force the point towards the middle. Is the attack surface of the adversary. And so now let's evaluate and discuss proximal consensus a little bit. So our protocol has two variants for it. The first variant is the processing nodes receive noisy inputs. They immediately at output time run a function, and they just broadcast their value to the processing to the controller. The controller runs proximal consensus locally on the function outputs it receives using the distribution model. But one thing to observe here is that if two consumers observe a different subset of those outputs, so let's say there's some faults that could happen, then two different controllers could result in different consensus results, and that could also cause the distribution that they're maintaining locally to diverge from each other. Does that make sense?
So you're saying if you had two different thermostats.
Yeah, so if you have two different thermostats and they each observe a different subset of the outputs, since they only need to wait for a certain quorum size, then they could result in a different value. And then when they update their distribution locally, that distribution will also diverge from each other.
And what is that quorum size?
The quorum size is 2f plus 1. Yeah. And I know there's 4f plus 1 now nodes. I'll get to why we need 4f plus 1 in 2 slides. So the point here is that we need a way to mitigate this divergence, because eventually they could just diverge infinitely. And so we also designed the coordinated proximal consensus variants. And again, we have a set of processing nodes consuming noisy data streams, but this time they run some Byzantine agreement on the logs first. And once they do that, they compute proximal consensus locally. And then once they compute proximal consensus locally, they would all conclude on the same result. And then they would all serially update the local parameters at the same time that they're maintaining. And this update is also consistent because they all produce the same proximal consensus results. And then they would update those models to the one-shot clients, consuming the same data stream from them. And this approach essentially mitigates the divergence. So every so often, the one-shot clients will receive an updated distribution that they can use. And so why do we need 4f plus 1? and this is a requirement under asynchrony. And the way to understand this is if we have 3f plus 1, then when at output time, these processing nodes will compute some function, broadcast that function to the controller, but the controller doesn't really know where, if it gets 3 messages, it doesn't know if the third message is from a non-faulty processing node or a faulty processing node. It can't differentiate between the two. For example, the third processing node, its message to the consumer or to the controller could have dropped or been delayed past the deadline that it needed to arrive by, or it could have, or vice versa. It could have actually received a good value, but it can't really differentiate between a non-faulty point or a faulty point. And so we must ensure in our system that we always have a 2f plus 1 quorum of non-faulty points, because that's how we can bound our Byzantine adversaries. And so if we add an additional processing node.
Sorry, Roy.
Yeah.
And so when you say we need to make sure that we always have a 2f plus 1 non-faulty, that means how many messages do you need to receive?
We have to receive 3f plus 1. So once we have 3f plus 1, this is the next animation. So once we receive, if we have 4f plus 1 processing nodes, then eventually one of the messages will arrive, and at least 3f plus 1 messages. Once the controller receives 3f plus 1 messages, it knows that there has to be a 2f plus 1 non-faulty quorum, and then it can proceed. But we also don't need to limit these controllers to proceed in the one-shot variant, because part of it is to guarantee liveness, is why we want an additional node. And so once you receive 3f plus 1 messages, you know that there's a 2f plus 1 non-faulty quorum, but you can also proceed in our system with 2f plus 1 messages if and only if the predictive interval you compute on the proximal consensus value, so its width, is less than an acceptable interval width that you defined. So essentially the protocol is configurable based on how much tolerance the system designer has, but it does provide a nice tolerance and a nice trade-off between liveness and uncertainty.
You mean uncertainty tolerance?
Yeah. Does this make sense? So to evaluate proximal consensus, we essentially considered the one-shot variant of the protocol, because if the nodes could eventually just synchronize on all the possible outputs that they're proposing, then they will definitely result in the best proximal consensus results. So if we show that the one-shot variant is, if we show the accuracy of one-shot variant, then inherently that will show that the coordinated variant will be just as good, if not better. So we evaluated the
I want to make sure I understood that. So like the one-shot variant without failure is your correctness oracle for everything else. Okay.
Yeah. And so this is kind of where we can see how we computed the noise and the values. And so essentially the client receives the same value x, but we multiply some noise factor to it, and that noise factor is different across all the messages that the client receives, but essentially the signal is the same. There's just a noise factor associated with that signal. And then the client computes the proximal consensus of the outputs it receives. And we also allowed it to train its distribution over five rounds, and then it would reset back to some non-informative distribution. So what I mean by non-informative distribution, in the first round, the client runs a proximal consensus with a Gaussian distribution with mean 0 and standard deviation 1. And over 5 rounds, it runs a conjugate function to update the distribution using the proximal consensus value it computed and using the argmax quorum, so the ideal quorum. And then in every round, we did compute the error. So every round, regardless of where the distribution was at, we computed the error of the proximal consensus results. And we did the same thing for Byzantine vector consensus, but this time we actually ran the Byzantine vector consensus algorithm, and those sensors essentially eventually converged on a single value, and that value was processed to the client. And we didn't assume we assumed a synchronous network, and we didn't assume any sort of messages being dropped in between those sensors. And again, in every round, we also computed the error. So does the setup of the evaluation make sense? So we ran our system under no attack first, and what we can see is that proximal consensus reduced the median percent error compared to Byzantine vector consensus by 56 to 65%, and we also lowered the maximum percent error by 23% to 30%. And we also ran enough simulations where we can be where the simulation results are statistically significant. And so we can use a z-score and an error margin, and we computed how many simulations we would need to run. And one thing I want to point out is we also ran this under different levels of F, and also as the error increases across the noise error increases. And so the mean is always 1, but the standard deviation increased from 0.02 to 0.12. And one thing to also point out is that these values were multiplied, so we assumed nonlinear noise. And
what was the vector consensus again? How did that work?
sorry.
The vector consensus, how did that work?
So they received the same. They received the same.
That's not right.
yeah.
The Byzantine.
And then we ran the vector consensus algorithm until it converged, and then that value was sent to the client, which they accepted, and then we computed the error.
And for these vector consensus algorithms, are these the ones that when there's more than one quorum that's possible, they take the average of all the
Yeah, so they iterate over like f plus 1, and then so you get 4 plus 1, and then you iterate over I think f plus 1, and then you take the average of that, and that would be your output for that round. And then
like if you get enough messages, you could potentially find multiple
Turbo points, and then you take the average of all the Turbo points that you got. So in under no attack, we did really well, and we also ran this under optimal attack. So in the proximal consensus scenario, we computed both the optimal suppressing attack in every round and the optimal inflating attack that an output could do, and we would take the worst one. And so that would be the attack the attacker initiated in that round. And we also did the same thing for Byzantine vector consensus. So for every Ferber point that they computed, we would compute the worst Ferber point that they could result in. And what we show is that we reduced the median percent error under the optimal attack scenario by 31 to 78%. And we also lowered the maximum percent error from 31 to 68%. And again, this was under the same f equals 1 to f equals 4 scenarios, and under varying levels of noise. The results were also statistically significant using a z-score and our error margin.
So about how many runs did it take?
So if I remember correctly, I think it's about 4,000. I think it's somewhere around 4,000 for 0.12. Yeah. But it's 4,000 times 5. So because each round was had 5 rounds. Or 6 rounds, so 4,000 times 6 actually. So another thing that we were curious about is how can we evaluate predictive intervals versus convex holes? And we essentially our predictive intervals captured the true output more than it did in the convex hole. And one thing that we kind of looked at was why did this happen more frequently in f equals 1 than when we tested this for f equals 2? And it's actually pretty intuitive that since the noise is Gaussian, the likelihood of receiving all the samples to the left of the distribution or to the right of the distribution, when you have 5 nodes when you have 4 non-faulty nodes is 12.5% of the time. And so in low F's convex hole approach, the convex approach would miss the true output more often in the predictive intervals, which is definitely more conservative in the guarantee. So once we had these results, like I'll talk about where we are today. We recently received a rejection to PODC 2 days ago, unfortunately, but we got some good feedback, and we're planning to submit elsewhere. We also have proximal consensus on archive, since we're really happy with where it is. But in our most recent results, we actually have a really good reason for optimism and motivation. So we analyzed the runtime complexity of proximal consensus, and we found that Byzantine vector consensus scales exponentially in D. So as in what number of dimensions increases, Byzantine vector consensus doesn't perform as well.
But this is just the point choice, not the protocol.
This is the point choice. And proximal consensus scales polynomial and computing the consensus results with f, d, and k. So we have like reason to believe that we can eventually improve. We can proximal consensus will scale higher in higher dimensions, and we also suspect that we can improve this n choose to f plus 1. One of the things that we're really thinking about is, can we identify the argmax quorum directly instead of iterating over all possible quorums? And if we can do that, then our runtime complexity and computing a proximal consensus value will significantly reduce.
We had an initial
We had an initial
heuristic,
one.
but we were wrong.
What's the value of the constant c normally?
Good question.
Yeah, so it's just a constant. I'm not entirely sure, but when c gets high, it is.
It's not one of the variants though.
Yeah,
Like, I'd have to dig out the.
It's not so. Yeah, it's not related to the parameters of the system.
I think it's like a artifact of the specific algorithm, like, I think, or something like that. Like, I actually think this is sort of a mix of the asymptotic analysis and the exact complexity. I think that for at least some, well, I don't remember. There's been some analysis of a few setups of the exact complexity, but mostly it is this kind of d exponential asymptotic complexity.
So after these results, we'll talk about what's next ahead. And so one thing that we're extending to is we only currently support Gaussian distributions and specifically univariate Gaussian distributions. And so we want to support additional kinds of distribution families that could arise in centrophysical systems or and other kinds of applications that rely on sensors. Mm-hmm. And so one of them is Poisson, so we can count the number of like Teslas that cross a bridge potentially, or do some count operation. We want to do the binomial to model success or failures. We want to model categorical distributions so we can model discrete probabilities. And then we also want to do exponential distribution for time until next event calculations, and then gamma distributions for time until the kth event, and also the Pareto distribution for modeling effects. But the point is why we think all these distributions are going to be more easier, since we already saw the Gaussian variant, is that all these distributions have analytical conjugate functions. And so that essentially allows you to take a prior distribution and then convert it to a posterior distribution given a set of observations. So the big question that we are still trying to answer in this regard is there a best similarity function? So one thing the similarity needs to do is it needs to be able to accurately reflect the values within a quorum and a candidate event. But each distribution has different properties, and so some distributions could be symmetric while others are asymmetric. And so how can we accurately represent the similarity in regards to each distribution? So this is a big question we're kind of thinking about. And I have slides that are not in this talk, but I can show an example of one example where this is an interesting problem to
How would you evaluate what's best?
So how would you evaluate what's best is essentially by analyzing the properties of the distribution. So, and
well, I mean, like the similarity similarity function, like its value is in terms of what? Like what is it good at versus not good at?
So essentially how we would evaluate how it would result, if we assume everything is Gaussian, we would evaluate what's the accuracy of using modeling the data as a Gaussian when it's really exponential, and seeing which one would result in less error in the simulation that we ran earlier.
Okay, I'll hold with the question.
So another thing that we're interested in is varying the number of dimensions. So currently we focused on univariate data, but we also want to capture correlations between data. And one of the interesting things is that if we wanted to measure like coordinate points, for example, our approach wouldn't work. And so we want to extend to multivariate distributions. And another thing that we want to do is that not all distributions are unimodal. And specifically, if we can use mixture models to represent patterns in data, then we can use the mixture model to model the patterns or seasons of data, for example, like traffic patterns in the morning, afternoon, evening all have maybe different meaning based on like the morning rush hour or inverse rush hour or things like that. And so we want to use mixture models to essentially to identify where we are in the distribution of the outputs, and then this will also allow us to tighten our predictive intervals, because instead of having one global variance for an entire possible outcome, we can identify that our outputs are representative of cluster 1, and cluster 1's local variance is much smaller than the global variance of the entire data set. And so we think this is going to be a really promising approach to improve our predictive intervals and identify the exact value that we conclude to. Another thing we're working on is Centauri, which is an implementation of the Proximal consensus framework. And the goal here is to build infrastructure to deploy it. This is one of the big feedback things that we got is, well, does it work in practice? And so our big
They asked that at Pod C, they asked that?
in middleware.
Okay.
Yeah,
I was gonna say, I'm
mainly-
surprised
mainly
Pod C
middleware, yeah.
people care at all.
Middleware gave us the best direction to think about. But the big one was, does it work in practice? And so we're currently building this infrastructure, and one of the complexities is to support both one-shot and coordinated variance. And eventually we want to be able to compare Byzantine vector consensus to proximal consensus. And part of this requirement is also, can we dynamically generate distributions for the system designer? And we don't necessarily want the programmer or want to expect them to be statistics experts. And so could we dynamically generate these distributions for them? And one reason why I think we can is that we essentially started with a non-informative distribution. And so Gaussian distribution, 0 mean, standard deviation of 1. And we computed the proximal consensus every round, and we used that argmax quorum to essentially to update the prior parameters into the posterior parameters using a conjugate function. And essentially what we can show is that even under both Byzantine and non-Byzantine attack, we are approaching convergence onto the unknown true distribution. So this is some results why we think we can offer this in our framework. Another thing that we're working on is the proximal consensus web GUI, which is used for debugging and visualizing simulations. And this was really started maybe like a year ago, where we were analyzing, well, how can we visualize what we're working on, and how can we visualize how much the conditional probability actually affects the prior distribution and the posterior distribution. And so we started building this web GUI to kind of visualize it, and it turned into this iterative project where we can now actually visualize proximal consensus.
It's a very generous we.
It's always we. We always talk in we. And the ultimate goal now for this is still iterative. It's not the main focus, but it is to allow system designers to simulate Centauri deployments. So instead of actually having to run it in the wild, you could just specify what kind of sensors you have, the distribution of outputs to simulate, or maybe even a data set, and then we can add noise to it and simulate the results and how the system would behave. And then the final interesting problem that we're thinking about is instead of having replication, can we compute redundancy and using mathematical properties of certain applications? And so this example here is called the platooning vehicle problem. And essentially what you have here is you have a bunch of autonomous trucks. All these trucks have location sensors and velocity sensors. And they also have sensors in the front and the back of the vehicle, so they can measure the distance between the vehicle in front of them. And the point here is that we want to keep the vehicles equidistant apart, and we want to prevent attackers from forcing one of the vehicles to collide into another vehicle. And so one way to do this is by building a system where you can essentially identify where the vehicle in front of you is, and then the controller will either slow the vehicle down using some braking system or accelerate the vehicle, meaning it's getting too far behind the platoon. And so one way to observe the distance between the first truck and the second truck is by just directly observing the location of this first vehicle and second vehicle. But you can use mathematical properties like physics to compute the current location of the vehicle by using its previous location times the average velocity over the time period, and you can get that vehicle's location again. And you can do the same thing for vehicle 2. And then the other way to include redundancy in your system is by the observations of other vehicles. And so you could ask vehicle 2, hey, what's your current distance, and what's the distance that you're detecting between yourself and the vehicle behind you? And you could do the same thing for vehicle 2, asking the third vehicle, what's your current location, and what's the distance you're recording from the vehicle behind you. And so here's 3 levels of redundancy to calculate the distance between vehicle 1 and 2. So this is one project that we're
And we
interested
would use those how? Like that, those would be the
So
samples.
so these indirect observations that you're making would be used. They would all be slightly like not consistent with each other because all these sensors would have some level of noise associated with it, and so we could use proximal consensus to compute the approximate location of the vehicles.
In a way that would be robust to the sensors on one of the vehicles having bird shit on it or whatever. I've brainstormed about things like that. This is great. This
Yeah.
is very cool.
Byzantine bird shit faults.
And I'll also want to talk about some background.
Where is the attacker?
Where's the attacker?
Yeah.
So for example, you could get a faulty. Let's say this vehicle is compromised.
Mhm.
The sensor could say, I'm in this location, and it's not really in that location.
Could equivocate about
So-
where it is,
Yeah.
but then other things that had prior observations of its velocity and location can provide multiple disagreeing and more truthful versions of where the thing is.
Yeah, exactly. And so essentially the point is that you can overcome malicious sensors, and even if some sensors like fail due to sunlight or some sort of attack that can happen on the vehicles. But the entire point is that you can use math to compute redundancy. And the back of mind ideas while we're working on these projects is, can we directly identify the argmax quorum? And one recent idea that came to mind was, can we use proximal consensus for data cleaning on big data sets? And one of the heuristics that we were using initially to try to identify the argmax quorum was Cook's distance, which essentially gives a score to each value in a data set on how much it influences the posterior mean, or the distribution of that data set. And what we tried was to run Cook's distance algorithm on the quorum and decide and essentially remove the values that had the highest Cook's distance score to them. But it didn't really work out as well as we expected. But one application that this could be useful for is, can we use proximal consensus for data cleaning, like Cook's distance is being used for data cleaning? And one example is if we can say, well, we want to get rid of a k number of values in our data set, can we run proximal consensus on and choose n minus k quorums? And then we would compute the most conditionally likely value of that quorum, and then the values not included in the ideal quorum would be removed from the data sets. So that's something we're kind of interested in. And then the final application is decentralized federated learning. There's a problem in decentralized federated learning where all the clients are untrusted or they're trustless from each other, but they all must broadcast their model updates to each other. But those model updates are not necessarily, some of them could be poisoned, and the big question is, can we use proximal consensus to bound malicious model updates? And this kind of connects to the multivariate case that we want to support. So the summary of this talk is that I introduced proximal consensus and motivated it. Essentially, proximal consensus is a Bayesian approach to approximating consensus. And the key idea is that we're computing the argmax. We're computing the most likely quorum and the most likely value. And we want to return the value that is most conditionally likely. I talked about discussing and bounding adversaries, and I provided empirical evidence that shows that we can improve accuracy compared to Byzantine vector consensus. And I also talked about future work and some of the things I'm working on, which is distribution family extensions, increasing the number of dimensions in our data, and also the number of models that we can support. I'll talk about Centauri, which is our framework, and the proximal consensus web GUI, as well as computing redundancy as another possible project, and some back-of-mind ideas that will be thought of as we are working on these problems. So again, thanks Owen for supporting me over the 4 years. And a big shout out to Daniel Spencer, who's actually a PhD graduate from the statistics department. Daniel was very instrumental in my early PhD of helping me learn statistics and formulating proximal consensus. And also thank you, Peter, Bruno, and Razvan for being part of the committee. And finally, my parents, siblings, partner, and friends for supporting me over the past couple years. So thank you.
bigger questions? Nothing from the peanut gallery?
Ike, you have a question?
No questions. Good job,
I
Ron.
thought you were gearing up for one.
Thanks, Ike.
You left the crowd speechless. I have questions, but I'll wait for the private session.
I can go for a few. I lost the. Can you go back to how you define? Are you trying to estimate the maximum posteriority of the quorums? I didn't get the. You said you don't have a conditional likelihood model. You don't have one. How did you end up solving it? Do you have a prior term you're using? Do you have any?
Are you asking about
No, if you go further forward.
forward?
Yeah. More. After you introduce the.
Is it?
It was when you first introduced the quorums in the equation.
Are you talking about?
Yeah, over there. Yes. So, yeah. So how did you end up solving it?
Yeah. So we can't actually compute this directly, the conditional probability directly. And the reason is we don't have a conditional probability table
Yeah.
between x and q. And so how we do it is by estimating it using a measure of similarity. And the similarity measure has this property where as they approach consistency, or the similarity is 1, meaning they're exactly the same, alpha goes to 0 and the conditional probability goes to 1. So essentially we're using similarity as a scale to the conditional probability.
And that's the likelihood of x given q. And what's the prior of a q? Is that
So-
uniform?
No, so we have some prior Gaussian distribution, and so for this given quorum, we run a conjugate update on the prior function or the prior distribution. Now we have a posterior distribution, and then we use that posterior predicted distribution to compute the independent likelihood. So the independent likelihood of x is based on a distribution update from the quorum.
I don't understand.
So we have a prior distribution
Over q.
over the output domain.
I would say there's an x distribution and an xy distribution. The x distribution is like the real output, and xy is the product distribution of the real output and the noise. We only get to see xy, and so all of the q's are coming from xy. And so,
So I thought q is a subset of the values that you choose. No.
Yeah,
Q
this is like a set of
values.
Yeah.
A set of
yeah, so
values.
that's really a joint, is that really a joint probability?
Yeah.
Um,
So at a certain point, this really doesn't have too much influence because then the joint probability of a large
so
quorum is.
isn't P of Q saying what's the prior likelihood of choosing a quorum? Right. That's what it is, no? P of Q.
Oh yeah, the probability function that we use is we take the prior and we update that prior using this quorum, and we have a conjugate function update. We can update the prior distribution into a posterior distribution.
Posterior over Q.
Yeah.
And that's what you use there.
Yeah, so this is actually, the P there is actually the predicted posterior.
And how do you do that? And how do you get the posterior?
So-
you have the equations on the slide.
I don't have the equations, but it's essentially a conjugate function.
We use the Wikipedia.
I can. Do
everybody-
you want to see the equations?
What's the family of the functions that you use for
So-
your prior?
So since a Gaussian times a Gaussian isn't necessarily a Gaussian, we actually model it as a normal inverse gamma distribution. And specifically, we use that distribution because it assumes that you don't know the mean or the standard deviation. And so when we start with a non-informative distribution, we actually set the parameters of the normal inverse gamma to alpha equals 1, beta equals 1, and the mean is 1. And then we slowly will improve that distribution over output runs. But we can essentially represent this XY distribution as a normal inverse gamma distribution.
You mean a normal distribution with
Or
parameters that are
yeah.
distributed. The priors are distributed distributed.
Well,
Normal.
I think the mean is a normal,
The mean is the same, yeah.
and then the variance is an inverse gamma distribution.
Yeah, so we're.
Do you want to see the equations?
One level of approximation that's happening here is that we are approximating based on some sort of rules of thumb that we found, but I would like to be corrected on if we're overusing them, but that for our case, the product of two normal distributions, so the noise distribution is Gaussian, and the output distribution is Gaussian. And for our case, where the relative size, or the relative magnitude of the mean versus the variance is good enough that you can approximate it, the product as a normal distribution. And so the output distribution, the product distribution we're modeling as a normal distribution with unknown parameters.
So this is essentially how we update this is that we have prior parameters, so we have u0, nu, alpha, and beta, and then we calculate, given the quorum, we update those parameters using these equations, and that would be our posterior
And when you say
distribution.
the quorum, you don't mean the just the indices of the numbers, like you said, like
So if
you
we
have
have-
the actual values,
The actual
the
values.
actual sensor values.
Yeah, the actual values that are measuring this domain. So for example, x bar is the sample mean, so essentially we would take the quorum's sample mean.
Yes.
And that is PQ in your.
We use this distribution, so the posterior predicted distribution, to calculate PQ.
Yeah.
And also PX. And specifically that is this it's a student T distribution that we use.
That's for P of X, or for P.
So the distribution, the probability is the student T distribution, and then we plug in what's the independent likelihood of X from this distribution that we're defining here.
So that is not the independent likelihood, I'm confused.
So when we ask what's the independent probability of the quorum, it's just the probability of Qi times the probability of Q2 times the probability of Q3.
Okay.
Because the reason we can do that is that the noise samples are independent.
Yeah.
So they really are independent draws from the noise. So can you go back to the similarities? So you mentioned like this idea of like maybe we need to figure out what the right similarity function is for different families. And I guess what I was looking for is like what does a bad similarity function look like here? Like what is it? How do you know when you've got a good one?
So I think that's subjective. Is a good similarity function is subjective, but in how we're defining it is that as the values become closer together, and essentially that the normalized distance between them decreases, they are more similar to each other. And so our similarity measure is essentially just a distance measure that we move on the scale of 0 and 1. So the equation is really just 1 divided by 1 plus the normalized distance.
What do you mean by subjective though?
So I think the point is that you could always try to find a better similarity measure.
But isn't there
Right.
a ground truth here? Like, isn't there a real conditional probability of?
The conditional probability is defined by the similarity, but the only requirement is that the similarity function returns a value in 0 to 1.
So you're saying it's not possible to evaluate, like, given some specific domain where we do have the conditional probability tables, couldn't we evaluate, like,
Yeah, you can
how well the similarity function is?
theoretically.
Then it just comes down to whether the domain that we were evaluating it on is close enough to the ones that we're applying.
Yeah, if you had that, you could, but
Okay.
I think the point is that you can't produce the conditional probability tables, and if you could, you would have.
Well, it just might not be, computational.
It also doesn't. Also, doing conditional probability tables is expensive, and we also dynamically update the distribution every round, and so that would add like a pretty big cost to the
Yeah,
system.
I guess I'm just trying to find a way of like,
So like
you know, evaluating the approximation bound that a particular similarity function is giving us.
yeah, I think how
Because essentially we're using it to approximate the conditional probability, so we should know how well it's doing.
yeah I think in the paper we state this is one of one of many possible similarity functions.
Sure, yeah.
Can you go a slide before?
Yeah.
I wanted to clarify a bit more on this, like why exactly you say we cannot model this distribution directly. We don't know the noise values.
You don't know the noise.
That we multiply x with, so we have x times noise. And you say we don't know the attackers, who the attackers are. But this is the likelihood. This is the So you're not talking about the posterior. It's the likelihood function, no?
Yeah.
It is, yeah.
But I'm a bit confused because I thought you could model likelihood is basically just a normal distribution centered around x times. Some kind of noise product distribution is centered around x, right? In which you actually and with the caveat that maybe we have some identity function in which you have an attacker. In that case, you have much higher value. If it's an attacker, you have this. Otherwise, you have that distribution instead.
I mean, basically, whenever we're doing these probability equations, it's on the assumption that, you know, what is the probability if these values came from an honest attacker, an honest node, because we're not trying to model the attacker probabilistic.
I think, as you point out in your proposal, you can't.
Yeah.
The only thing you can do is assume that they're all honest.
Yeah.
But yeah,
So if it's an honest, we can model it because it's
Right.
just like a distribution.
Right.
Then we don't know the attacker. We can sort of have a hidden variable denoting which node was compromised, right? And we can also say that that's a latent variable. And so then it becomes a p of x given q comma a, and a is like a label as a hidden variable, says if this node is malicious or not. And then you have different values of a, if a is 0, if a is 1, and you have different.
I think that there's an inherent assumption about plugging in any of the adversarial nodes in there, is that their historical behavior will predict a future behavior, and you can't do that with a Byzantine. So like, I think any kind of statistical model of a Byzantine adversary, in fact, I was reading some related work here, and I was pounding the desk because they were building like essentially a reputation score for which are the Byzantine nodes. And you know, you just wait until you have a good reputation, and then you blow everything out.
Right.
Yeah. Yeah. So that's actually like an explicit design principle was model everything around the Byzantine nodes and see, you know, who's trying to hide.
Yeah, and then the big point is that the worst the Byzantine node can do in this system is based on the worst non-faulty points. So essentially we're inherently bounding those Byzantine adversaries from being just as honest as the worst honest points, or be ignored, and the value won't have any influence.
Isn't the one-shot protocol then more powerful? Like in the one-shot protocol, the adversaries don't know what the guesses are of the other nodes. And so if I were an adversary and it was the one-shot protocol, I wouldn't be able to use knowledge of the most dissimilar honest replica.
We assume that they know.
Yeah, I mean, in our evaluations, we gave them.
Yeah,
You just assume they're omniscient.
We
So that's a moot
we
point.
let
Okay,
them.
sure.
We let them have optimal attacks.
Okay.
yeah. And it's funny you use that word because that was a correction from one of the middleware reviewers, was to specify that they're omniscient. We didn't explicitly say that, and then
Oh, go ahead.
I have one. You have a lot of listed future work and back of mind ideas. What are your highest priorities right now? Because that's a lot of work lined up.
As
So
someone that's trying to graduate
Yeah.
soon, I'm worried about.
So right now, the big thing that we're working on is building Centauri, and I've also started working on distribution family extensions. So that's kind of the two big things that we're working on. But I think one of the focuses that we're kind of recently started thinking about was mixture models is also a top priority. So we're essentially trying to like expand proximal consensus to be able to simulate it in more complicated environments.
Until somebody recognizes that it's publishable.
Yeah. Yeah.
By the way, if the committee has any suggestions on venues for this.
No, I do. So DISC, the abstracts are due May 7th. So if
Oh,
you have
yeah.
a paper that you dressed up for Pod C for some crazy reason, DISC, it'll fit right in. So
okay.
you might be able to just flip it directly.
That's
If you
a
don't
great
want to
idea.
flip it directly, if you want help and you want somebody to look at the Pod C reviews, let me know.
If you have the bandwidth for that, that might actually be really helpful.
No, let me look at the reviews and see if I can help.
Okay.
But I have a couple suggestions that maybe I'll save for the private meeting.
This is a good one. Yeah.
Mhm.
DISC 2024. If you just say like DISC conference,
Well, so just to keep us on not too far off time, are there any other questions from the public?
None for me.
All right.
That was the top.
All right, well, let's thank Roy again. And then we will boot out.